It's a great pleasure for me to welcome my colleague and friend Angela Olinto from the University of Chicago, where she is, I think, the Albert Michelson Distinguished Service Professor, which is and Dean of Physical Sciences there now, which is a nice counterpart to our Peter Michelson, who is also Dean of Physical Sciences, I suppose, sort of here. And Angela was from Brazil and was an undergraduate there, I think, and then a graduate student at MIT, where I think you worked with Charles Alcock on strange stars, if I remember correctly. And then went to Chicago and Fermilab in various roles, including chairing the department not once but twice, and also I think being the first woman professor there, and of course the first woman dean in Chicago. And Angela's scientific interests have been largely in the areas of sort of what you might call nowadays extreme astrophysics. This is high energy particles, neutrinos, cosmic rays, dark matter particles perhaps, in astrophysics, and has contributed to the theory and phenomenology of this. And more recently, she has been very heavily involved in, firstly in the data analysis, but then very much in the planning and leadership of missions, ones that are have already operated and ones that are planned for the future, which is what she's going to tell us about this afternoon. She's going to tell us about observing the highest energy particles with space observatories, and in particular two that are very much occupying her at this time. And so without further ado, I'm going to hand it over to Angela to tell us about these exciting projects and the science life behind them.
Lovely. Thank you so much, Roger. It's so nice to be back here, and it's been a wonderful visit with lots of interesting conversations, and I'm definitely inspired by the next generations, and some of these things that I'm doing now I'm pretty sure are going to happen for the next generation. So please, unless I take tons of vitamins and find some other way to continue. So some of the ideas here are really things that, so I'll give you a sense of what we know and why am I spending time looking into future options for how to further the field. And as Roger mentioned, the field is understanding the origin of particles, of very extreme particles. And the two projects that I want to end today with are the two that are occupying my time, as he said. One is POEMMA, which I love the acronym. In Portuguese, POEMMA means poem. But you spell it with one M, so for the younger generations, if you come up with good acronyms, they should spell something that you recognize but not identical, so you can Google it and it only shows up as your thing, versus lots of poems in Portuguese. So the two M's are very important. And the other is a bad acronym, so that's the ones you shouldn't have, but you know, it's history. And it's EUSO, it stands for Extreme Universe Space Observatory. And SPB stands for super pressure balloon. And EUSO is a long-time collaboration that has changed its goals over time, so we keep adding specifiers to EUSO. And so I'll tell you about that soon. POEMMA stands for Probe of Multi-Messenger Astrophysics. And the goals, I can't use that, I have to stand here. It doesn't work, the mover. The goals are written here. So these are, there are two questions which are really astrophysical in a sense, which is what are the sources of the ultra-high energy cosmic rays, which we write UHECR as an acronym. And what are the sources of cosmic neutrinos? And the second question is something that we knew there would be cosmic neutrinos, but now we know they're there, and that's thanks to IceCube. But we still don't know what are the accelerators of those neutrinos either. But then why I care so much about the extreme, there is beautiful astrophysics that we all love, but there's also interesting possibilities for high energy physics, which is where my career started. It started with the death of the SSC, and some of you might know what that acronym stands for, Superconductor Super Glider. And going around the problem of how do we reach much higher energies in some alternative ways, the universe to me seems like a really good place to do that kind of science. We just need to know the accelerators better so we can start knowing where the neutrinos started and how do they make it here and how they interact both throughout the universe but also on Earth. So having beams of neutrinos above, you know, PeVs all the way to EeVs will be a lot of fun to future generations. But let's start with last century and the beginning of it, so more than 100 years ago. Cosmic rays were defined as such by Victor Hess as this balloon flight. So ballooning has been around in the field for a long time, and the balloon flight that I'm showing here on the plot is showing how the cosmic ray flux, which was then called the ionizing radiation, goes up as the balloon goes up. So this is chamber 1 and 2, and the flux going up with altitude. And that means that something, you know, this radiation is coming from outside the Earth, and the atmosphere is protecting us from it. There's some radiation, obviously, on the ground. For definitions purposes, astronomers like to do multi-wavelength observations, and this is what multi-wavelength might look like, combining radio all the way with gamma rays. So we here in Stanford, everybody should know what the Fermi Gamma Ray Telescope looks like, and ALMA as a radio telescope. So this is, you know, many, many orders of magnitude that we use photons or electromagnetic radiation to understand the universe. When you add cosmic rays and neutrinos, you double the number of orders of magnitude in energy. So if you translate the photons to energy here, this is the kind of doubling of the range in terms of cosmic rays, and then neutrinos starting to become interesting in this energy range. And I put pianos, which I think is what Roger likes to have also to talk to the public in terms of translations of orders of magnitude. My husband, who's a musician, has a real hard time with that because obviously pianos play the same notes. So I have to abstract what it means, but you know, we've had infinite discussions. And if you go to the other end, you can triple the number of orders of magnitude that one can observe the universe with by adding the gravitational waves at the other end, because these are longer and longer wavelengths all the way to pulsar timing. So, you know, if we want to be really observing everything we can about the universe, we would be doing things here, here, and there, and that's what multi-messenger means in astrophysics these days. So it's not just multi-wavelength, but also using other messengers. Now, cosmic rays are one of the difficult messengers. They are, you know, very familiar. They've been with us forever. But the big problem of doing astronomy with cosmic rays is that they don't point back to the source. They are isotropic. These are charged particles dominated by, say, protons at the lowest energies. And those charged particles go through magnetic fields, and they lose track of where they came from by the time they reach us. Here is what the cosmic ray spectrum looks like in a simplified, sort of putting all kinds of data together. As I mentioned, it's very interesting that it has so many orders of magnitude, so we have a lot of science to be done in this range. The tough thing from the experimental point of view is that this is a steep falling power law, so you get, you know, kind of a power law. You get 30 orders of magnitude in flux, so you can't use the same detector to get all that story. It also doesn't tell the same story everywhere, so at low energies, the solar influence is very important. And so you do, you know, basically the solar system will influence the low energy cosmic rays because of the magnetic field of the sun. And we think that most of the spectrum is galactic cosmic rays, and we know that at the highest energies it's extragalactic. How the transition between one and the other happens is still to be determined. We don't really know. The nice thing about the low energy ones is that they have high fluxes, so you can go directly and measure them, and this is done in experiments both in balloons but also most recently in space. And AMS is sort of a wonderful big detector that can see lots of cosmic rays in the low energy range, and it's sitting on top of the ISS, the International Space Station. The rest of the spectrum is done on the ground, and the ground detection is done indirectly and basically uses the fact that we have an atmosphere, and the translation from the top of the atmosphere to the bottom gives you a way to detect these particles. So here's a compiled spectrum, a more recent, so this is from last year, ICRC, which is a meeting that, international meeting of cosmic rays that everybody gets together. And this is a spectrum multiplied by e to the 2.7, so that, you know, steep falling power law is taken away, and you see something which is somewhat flat with lots of bumps and wiggles. There is what we call the knee. Now it's become the first knee because there's a second knee, the ankle, and a drop. And what you might notice is, there is some overall agreement on the shape, but then if you go to, very sort of zoom in, there are systematic offsets. For example, at the highest energies, Auger in black, which is the experiment I was involved for 20 years, it has a 14% scale in energy compared to, due to systematics, because you have to use that uncertainty to sort of reproduce what you're measuring, and I'll show you how we measure soon. Underneath those bumpy rides on the spectrum, there's also a bumpy ride on the composition. So in red is protons, and then let's look at red and blue to simplify our composition. Blue is iron. You see that there is something peaking on the proton. So proton is dominant at low energies, but then iron seems to take over, and then it gets pretty confusing over here. And this confusion is probably due to this being extragalactic, and in between being some transition between galactic and extragalactic, maybe an intermediate scale, maybe different sources. So we don't know exactly. The challenge is to measure these things. So here is fluxes, typical flux around the knee, about 1 per meter square per year. The most exciting particles for me are 10 to the 20 electron volts, and for that, the flux is 0.1 per kilometer square per century. So that's a lot of time, or a lot of kilometers square. And you're definitely not going to fly lots of kilometers square detectors. The good news, though, is that you don't catch the one particle. You basically sample the particle through a calorimeter called the atmosphere. So the atmosphere is a calorimeter. It takes one particle, say in this case a 10 to the 15 electron volt event that Pierre Auger in 1937 detected. It makes a cascade of other particles, and by putting detectors on the ground or observing this actual light from this cascade, you can infer the energy of the primary particle and even its composition. So here is one of these simulations just to give you a sense. In this case, it's a simulation of a proton of 10 to the 14 electron volts. And here's us just following the center of energy of this shower. Here's the particle distribution on the ground. It's dominated by electromagnetic in red, so electrons, positrons, and photons. You also have muons coming as the second type of particle that reaches the ground. And for this kind of energy, you could space, at every 100 meter with a detector, and the detectors will all be hit together by something coming, just straight down, like in this case. There is also the evolution of the actual shower with altitude, and this is shown here. And the reason this is important is because there's another way of detecting these showers, which look at the fluorescence of the atmosphere. So this is what it will show. The electromagnetic cascade can fluoresce, and something is interfering. And that fluorescence can be detected for, say, a proton, and you can actually know that this proton had an integral under the curve in energy of 10 to the 14 electron volts, and it peaked at this altitude, which means that it's a proton and not iron. So iron with the same energy has now 56 components, so it will interact sooner for the same energy, because you have now 56 pieces of protons interacting in the atmosphere, so it will peak a little higher for the same energy. Energy per baryon should be similar. So the way we infer both energy and composition is by observing these extensive air showers, as they're called. And in Auger, which I'll tell you in a second about, we use fluorescence for the shower evolution, and we have particle detectors on the ground to get what was left from the particle shower as it reaches the ground. If you I'm sure you've heard of gamma ray detectors on the ground that look for showers also. They look at the Cherenkov, which is coming on the forward direction. And this is what some of the high energy gamma ray detectors do, telescopes do. And we will be talking about this too, because the two projects I'm talking about will use both fluorescence and Cherenkov to understand what's going on with these particles. Okay? So the leading observatories are the Auger Observatory, that I will mention again, over here in Argentina. Auger has 3,000 square kilometers, is the largest one, and it's been constructed in early 2000s. And has been operating since, and it basically, as I'll show you, it's a modular thing, so you keep operating. 2008 it was complete, and then it's been operating since. And telescope array in the Northern Hemisphere in Utah is a quarter of the size, and is now being expanded to reach the same amount of basically area. So here's the telescope array. the version that it had before it starts expanding, which is happening right now. It has detectors, 500 scintillator surface detectors spread in this area of 700 kilometers square, and then 3 telescopes that oversee the site in fluorescence. And here's one of these fluorescence showers. You can see the 2-decker, which is this telescope, showing a shower developing here and moving through, if you can see on the actual data. And here is the Pierre Auger, and Jim Cronin was the guy who brought me into this project by asking the following question: what energy do we have to detect particles in so that the magnetic field gets out of the way, so that we can actually point to the sources? So the dream is that we will reach energy so high that we can point back from the shower itself and know the source. And that is when the magnetic field gets out of the way. Eventually, magnetic fields are fixed and the particle energy gets higher and higher. So if you get to, say, 100 eV, so 10 to the 21 electron volts, for example, say 1,000 eV, then you actually should be able to point back. But the question is hard because for astrophysics, there are 2 questions. We don't know the composition ahead of time before we were building Auger, and now we know the composition due to the measurement. But also, if it's iron, it will take longer, obviously, in energy, because the Z is larger. And the other question is, what are the magnetic fields in when there isn't much stuff, right? So between galaxies. And now we have beautiful simulations starting to set those numbers, but it is pretty iffy to make a prediction. But you would expect that, around 100 eV, which is 10 to the 20 electron volts, we should be able to point back. Now, this is something we did for outreach, and so each of the yellow dots is a detector, a particle detector in the ground, and so you see the shower lighting up some of the yellow detectors on the ground, and then you see something quite interesting, a Superman effect, which is that the telescopes send light to the shower. Should be the other way around. So when you do outreach, you have to pay attention. Sometimes we sleep, and then people are believing that X-ray vision goes the opposite direction. Anyway, sorry about that. But anyway, so here is an actual image of the site. So this is one detector in Pierre Auger, another one. The distance between the detectors is 1.5 kilometers, just below a mile. And then around the site, that 3,000 square kilometers, we have 4 telescopes, and those telescopes observe the showers coming down at night. So the duty cycle of the ground array is 100%, while the duty cycle for fluorescence is 10 to 20%, depending on the year. But with all this work, we can put together the spectrum that I showed. So Auger is the black dots over here. And you can see that there is a green measurement, which is the telescope array. And within error bars, you could probably rescale the energies because we do reconstruction differently, and then it will be pretty much in agreement most of the place until it gets to the highest energies. You see the statistics for telescope arrays a little bit lower, but it is possible that around 10 to the 20, there are more cosmic rays in the northern hemisphere than in the southern hemisphere, which for a Brazilian is very unfair. Seems like even the universe prefers the northern hemisphere. That's not fair. But anyway, we don't know yet. They are growing telescope array to increase that statistics, and then we should be able to know if there is really more sources in the north, which is possible. All right, so let me give you, just for the particle physicists, here's where LHC PP collisions are at 10 to the 17 lab frame. So this is obviously a central collision. So the physics that we know in the lab for proton-proton collisions is ending here. So all this stuff is stuff that we don't have laboratory measurements. But we expect that the central collision in these sort of reactions are going to be very similar to basically most of the collisions will have interesting things happening on the sides. So if you're looking for the Higgs, for example, it's unlikely that that will matter to the cosmic ray interactions, right? So most of it is basically sharing the energy with billions of particles, so you end up having mostly normal physics, at least for the collision in the atmosphere. So that's what we do, but we have to also know if we're putting protons in the beam or something else, and that gets a little more interesting. Now, one thing that Auger did, aside from doing this beautiful measurement of the spectrum, this is all Auger, by the way, so you see the second knee here, the ankle, and the turnaround. The other wonderful result is an extragalactic component that is at least dominant at 8 times 10 to 18, so 8 eV. Just before 10 to the 9 electron volts, we have a dominant component we think is extragalactic, although dominant is interesting word because the dipole is not that big, but I'll show you in a second. So it is possible that extragalactic sources are dominating at earlier stages, or it is possible that is not. There's still some galactic over here, although from astrophysics we don't expect much galactic contribution at those energies. And that's based on this measurement, which is finally we see an anisotropy at these highest energies. And we believe this anisotropy, so this is a dipole for basically events above 8 eV, and it's just a 6.5% dipole. It does have sort of a general direction towards what the 2MRS catalog would say, except for that it's shifted over here by this arrow. And these are what you expect to be shifted by some models of the galactic magnetic field. It does have an interesting perpendicular nature to the supergalactic plane, but this is so the absence of the center of our galaxy, or the galaxy showing up here, is what we use to say that this is really an extragalactic component. So we're finally in extragalactic territory. We might have been at the extragalactic territory a little earlier, but this is the one measurement that people use to think this is really extragalactic, which is not surprising. That's what we expected to be the case, given gyro radii and typical magnetic fields. The other thing that's happening is just when we're running out of data, hot spots are coming up. So we do seem to be, the answer to Jim Cronin's question is around 50 eV roughly. So this is when we start seeing interesting correlations and hot spots in the sky. But then the statistics gets really tough. So here is what we have from Auger this past year. A distribution, and by the way, the white pieces are the parts of the sky Auger does not see, and obviously this is where the telescope array can see things because it's in the northern hemisphere. So Auger has this sort of 4.5 sigma correlation between the data above 32 eV and starburst galaxies. And we were just having a conversation how to label starburst galaxies, but they are trying to follow some of the astronomers' pointings here. And then there's a 3 sigma gamma emitting AGN, active galactic nuclei. So it's not clear exactly what are the sources, but it is clear that it's deviating from isotropy, and it seems to be correlating with some of the most powerful sources out there. So the question now in the next run from Auger, the next data, is of these correlations, will the active galactic option win versus the starburst galaxies? And we were just discussing how Centaurus A might have both in them, and anyway, and that doesn't explain the whole mechanism. It just tells you that the distribution of the sky seems to correlate with one type of galaxy more than another. Okay, so that's fun. And I had to put the Event Horizon Telescope image of M87 there just because it's so pretty. All right, so the challenge is that when the sources become easy to find, we run out of data, so it's statistically limited, and this is why I'm working on these projects, to make some better measurements at the highest energies. The turnaround is an interesting question. Why does it dive? And does it dive forever, or does it recover? Those questions have to do with what are the accelerators? Is this the maximum energy of the accelerators? Or is it the effect due to Greisen, Zetzepin, and Kuzmin, the GZK effect? People expected before the measurements began, most people expected, some of us already thought it could be iron instead, but if you were thinking, okay, let's just inject the most common element in the universe into all accelerators around and try to reach the highest energies, you're likely dominated by protons. protons that are at these energies traveling through the microwave background. So Greising, Zatsepin, and Kuzhnin came up with that just after the microwave background was discovered. They will lose energy by pion production, and they will have this sort of termination, or at least only the very nearby sources. Here's the proton energy loss length. This is sort of the size of the universe in blue. And you see that, for low energies, the whole universe is available to us. So at 10 to the 18, we see all the cosmic rays in the universe. When you get to 10 to the 21, you only see within 10 megaparsecs. And this is quite a very steep change. So this may be the origin of that turnaround. And that works for protons. For iron or any other nuclei, it would be photodissociation. So there's an equivalent. And actually, those three gentlemen mentioned iron too at that time, which is something people forget sometimes. But suppose they are protons. If they're protons, and similar things will happen with nuclei, they will not only lose energy, but they'll also be producing some gamma rays, which will not go very far, because these are very high energy gamma rays. They will lose energy to the same backgrounds. But you have neutrinos produced. So, the idea of looking for neutrinos was very soon, well, 69, proposed, and that's another indirect way of looking for both what are the sources, but also how does the propagation change neutrinos into protons with higher energy into neutrinos. And neutrinos, as you know, this is a table just in case you forgot what the neutrinos are on the particle data book. They're right down in the bottom here. Neutrinos are very exciting for astrophysics. They generate Nobel Prizes. So you have 2002, the first astrophysical neutrinos coming from the sun, and supernova 87A. Then the dream of using neutrinos to do a particle physics, in that case of discovering neutrino oscillations with the solar neutrinos and the atmospheric neutrinos. That's another beautiful Nobel Prize. So right now, I was just mentioning that cosmogenic neutrinos, the ones that are produced at these propagation, will be an interesting thing to study. However, the flux that is shown here is for protons, and as I showed you in this bumpy plot before, it's very likely we have iron, and then the flux is actually much lower. So it's going to be tough to detect those, but I think they're definitely worth detecting. And then there's the one in the middle, which has been detected by IceCube, as I mentioned before, and here's IceCube, and here's the astrophysical ones. And this is just a sketch, because we're going through many orders of magnitude, but just to orient everybody, that astrophysical neutrinos become seeable once the atmospheric neutrinos get out of the way. And so when you're right at that transition, it's hard to know which neutrino is astrophysical, which one is atmospheric. As you go to higher and higher energies, pay attention, for example, at 10 PeV, where I'm going to be focusing myself on, then you get only these astrophysical neutrinos, and then eventually the cosmogenic ones. All right, so here is the IceCube neutrinos that have this, both the muon neutrinos and the other types, the cascade types. And here in blue and in green are the atmospheric neutrinos, and the mixture there says that you don't know for sure which neutrino is which, but eventually at the higher energies, at PeVs, it becomes easy to see. All right, so how do we answer the questions I posed? There are ways to do this, right? So the question of what are the sources of the ultra-high energy cosmic rays, you can definitely do lots of beautiful theory, like those we were discussing today with Roger and everybody else that's working on this here. But I think experimentally you want to measure the spectrum, the composition, and the anisotropies above 10 eV. So an eV is 10 to the 18, so above 10 to the 19 eV is when things starting to simplify in the sense that we have more direct measurements towards the location in the sky. The spectrum is dying, so that means that only the very nearby sources are contributing. And you have now, reached iron, and we don't expect gold in the cosmic ray, so that's it. We have one composition. So that's one way to do it. So that's what I'm trying to do with these projects. And the second question, you want to do a multi-messenger coincidence. I think that would be super fun. We have the one example of a gamma ray blazer flare in gamma rays and maybe a neutrino detection, but it's on the maybe because we are still close to the atmospheric stuff. So if we can have a trigger, say from a gravitational wave or from a gamma ray, we have to decide which objects to follow, and then we can actually measure the neutrinos, which is what we are working towards, at 10 PeV. Then we have interesting science to do. And again, we want to know the physics and the astrophysics at these highest energies. I didn't mention that in my first slide, because there are interesting things that could happen that will surprise us, but we want to reach those highest energies some other alternative way than building accelerators that go around the Earth, because that's a little expensive for now. All right, and that wouldn't be enough. It has to go around Saturn. No, sorry, it has to be around Mercury orbit to reach that delivery. All right, so POEMMA. I introduced you the acronym, Probe of Extreme Multi-Messenger Astrophysics, and the multi-messenger in our project is ultra-high energy cosmic rays and neutrinos, and tens of PeV neutrinos. Let me see, right. Oh, I wanted to mention probe is a specific word in NASA. It means below $1 billion right now. Okay, so I have to design something which is below $1 billion, and the way we got this project designed was through a competition for ideas for the next decade. So it was an Astro 2020 call for studies of probe class missions, and we were one of the 10 selected, and we did this beautiful study. So here's a team of folks that I feel like the conductor of an orchestra. This is the orchestra. I don't play any of the instruments, so I have to find the right people who play the right instruments to get it done. And we had a great time. And the team has folks from Auger, EUSO, Auger, Telescope Array, Veritas, CTA, Fermi, and Theris. So lots of folks in yellow are the non-US based, and then a large team of US. So the two techniques that we planned for was one, to really move the knowledge in ultra-high energy cosmic rays by 1 or 2 orders of magnitude. We need to do something very, very large. So 3,000 square kilometers in Auger is sort of this big, so we want to do 10 times bigger. And this is what POEMMA will observe if we were to point both of them down and use it as stereo reconstruction of the showers. Okay, so this is the smallest area on the ground by just putting it pointed down in zenith. For the neutrinos, what we're doing is basically looking at the limb of the Earth, and we're up at 525 kilometers. So the limb of the Earth is roughly at a distance from the east coast to the west coast. So I'm actually with POEMMA looking at us here in California. So that's the scale of the amount of atmosphere. And obviously, I would be looking for neutrinos coming from the limb, and I'll give you more details on that. But at the same time, I can also look at ultra-energy cosmic rays coming down, but maybe less precise when we're looking in the same direction. Here are the two teams of engineers at Goddard Space Flight Center that helped us design this. So we had an instrument team and then a mission team. And here's the final instrument. I started with a much bigger telescope, and then the price tag came down, so we had to downsize. So the decision was, so the bigger the mirror, the more lower energy you reach, right? So if you want to go to, an EUV, you have to have a 10-meter mirror. And these mirrors are not optical mirrors. Think of them as antennae, because they don't need to have high RMS. They can be really rough. They're buckets that collect photons. That's all we need. And the 4-meter diameter is determined by the launch vehicle and the idea that we want to have 2 of them. So we want 2 in the same launch vehicle for the same launch. And there's an Atlas V that can accommodate those 2, and that was done during the mission accommodation. We are trying to have the widest field of view because we want to see the most amount of atmosphere. So Schmidt design for the optics was what we did. So here's the camera, there's the mirror. Then we have basically a beautiful filter, or what do we call it? I keep forgetting the names. A corrector lens was what we called it. And that's a 3.3 meter. There's an infrared camera in the green little spot here, and we are building those kinds of cameras in Chicago. And then we have a beautiful camera, which I'll show you in a second in another slide. So here's the camera. So, you know, we have a mirror and it focuses the light on this camera, and what we designed was a hybrid camera, a camera in blue of multi-anode PMTs. Those are what we use to look for ultra-high-energy cosmic rays. Basically, each of these, you know, so here, this is one that we built for the balloon program, which is where we're flying these things. And I'll show you later how they observe these cosmic rays. And basically, a shower will develop in maybe 1, 2, or 3 units at most. So you have lots of little showers happening in these blue boxes. And the total number of pixels here is 126,000, 27,000. All right, so this is one piece, which would be the one that you observe ultra-high-energy cosmic rays with both eyes. And then, and by the way, the time scale for this kind of measurement is about a microsecond. So it's a video of a microsecond in the ultraviolet that you see the light going through, and then you get videos of these lines. And if you have 2 lines, you know exactly how to reconstruct the orbit. If you have a mono detection, you know 1 line, but you don't know where and what was the impact parameter of that line. Okay? So 2 is relevant for example, if you want to look at composition. If you want to look just at direction in the sky, mono detection would be fine. And so if one of the eyes don't operate, we still have interesting data. In red is a now 10 nanosecond time scale detector, and we're developing this for the balloon payload now, and that is based on silicon PM photo multipliers. And we designed it so that, you know, at 9 degrees of basically observing in the limb direction. So the idea is you point towards the limb and you can see showers coming upwards from that area in Cherenkov light, so it's optical instead of ultraviolet. So here's one possibility for pointing those things, is a cross-eye version. So you have 2 POEMMA satellites in a cross-eyed situation in which the volume in the middle you use in red to look for ultra-high-energy cosmic ray traces. And then the dark green and the dark blue, these are just, blue and green are the areas that you see mono, so only with 1 eye. And you will see from the limb of the Earth, upgoing showers coming towards you. Okay? Hopefully that's clear. All right. And then the mission itself, it's a 5-year mission, and you have the deployment of these 2 folks, so they get, you know, squeezed together, and then they basically deploy in, you know, with elbows that snap in place, and then they sit around for 5 years looking at the directions we would like them to look at. And I'll show you a little bit more about target of opportunity things. I already mentioned it's 525 kilometers. It's roughly 28-degree inclination. Nothing particularly difficult. None of these things. I mean, the only thing we don't need to synchronize things very precisely. We do want to know what time it is in each observatory to 10 nanoseconds, but we don't need to be precisely at any position in particular. But we roughly want for the stereo to be about 300 kilometers apart, and for when we're looking at the limb, we can be a little bit closer so that both of those telescopes see the same Cherenkov cone coming from the edge of the Earth. So in terms of ultra-high-energy cosmic ray exposure, we would be an order of magnitude improvement if we're looking towards the limb, and, you know, an order of magnitude even for nadir, but, you know, basically a little bit of a bump from what an extrapolation of going forward with telescope array and Auger forever means. Who knows if they'll go forever. There's nothing in the books yet to do something on the ground bigger than them. It's really difficult. We tried, Roger remembers, the northern site for the Auger Observatory would be 10 times bigger, but basically the excitement on the technology part and on the actual implementation, which is really challenging with humans to take over so much square footage of people's lands and put detectors on them, we did not go forward. So here is what ultra-high-energy cosmic ray results of this effort look like. So we have a very constant exposure in the sky. So this is at 10 to 21. It looks very flat. Auger in green sees the southern hemisphere. Telescope array in black sees the northern hemisphere. We see both hemispheres, and we should be able to, for example, detect the nearby starburst galaxies very well. So this is using the Fermi-Lat ones, but anyway, this is just one example of the precise map in the sky that one could do with a lot more cosmic rays around 10 to the 20 electron volts. So 1 order of magnitude or 2. And that will be brilliant because then we can actually discover where the sources are coming from. Then we still need to figure out the acceleration mechanism, but we will know where they're coming from, which objects in the sky. And then the fun part, which we were not totally ready, and we had to do a lot of calculations to make sure that we were doing the right thing for the neutrinos. So the basic principle has been around, right? So you have neutrinos coming from some source. Usually an astrophysical source will produce electron and muon neutrinos, but because of oscillations, we'll get new taus also by the time they get to us. So something like a new tau coming from the other side of the Earth can cross the Earth and leave, or it can interact and produce a tau lepton, and that decays at the right altitude to create a shower that we can observe. Okay? So each of these pieces need to be calculated, which many groups have done pieces of, and we put it all together. And you know, the idea is we would know there's a source in some part of the sky, point the two telescopes in that direction, and just look for Cherenkov light coming from that source. Okay? So what are the sources? This is a big table, and we spent some time, and the paper should be, it's already in the archives, an earlier version when we did more work on it. And in bold face, it's hard to tell where you're sitting. These are those that we can sort of predict we will see with higher chances. And you know, some of these models, I will not put tons of money in them, some I will. So for example, Kei Feng, one of our students and now your postdoc, I put money in her model. And so in her case, it's a neutron star merger, and we would see something like 24-ish neutrinos from that event. Some events like a black hole with some interesting accretion disk, blah, blah, blah part, might get orders of magnitude higher number of neutrinos. Laser flares only if they're nearby enough, because you know we go to 40 megaparsecs on the solar flares. Tidal disruption events, you know, could be a really good source too, up to 100 megaparsecs or so. So there's a list of possible transients that might generate neutrinos, and I'll show you a little bit more of those in a second. And the idea is, so one of these things happen, we get an alert, and we point. Some of these models produce neutrinos immediately, others will produce it weeks or months later. Obviously, with weeks and months later, we have more time to point in the right direction. So the way we would do this is, you know, there are sources in the sky, and if you sit in POEMMA, the sky is rotating, and we would see the sources either because they seem to be rising or setting on the other side, if you're looking at a source which is parallel to the orbit. But there are some sources that POEMMA will see for a lot longer period because they will be kind of below the limb, just like the sun is in the winter in the South Pole. Right? So it sets for a long period, so those sources we could see for much longer periods. And then there are some sources that never sit, just like the sun in the summer in the South Pole. And that is the region of the sky that for a given time of the year we will not observe. So translating this into a plot, here is two types of models. Some which are longer bursts, like the one that Kei Feng, who's postdoc here, worked out with Metzger. And here are some of the lines of the POEMMA sensitivity and some of the limits from Antares, Auger, and IceCube. And this purple, you know, I think it's purple, but you know, the looks pink to me right now. But this sort of band is a range of what you could see in the sky. And the dark part is the one that you see most commonly, and the lighter part are some of the places that you see a lot, and then sometimes you see very little. So let me give you one. This is short bursts over here, and this is long bursts. And this is another model, the Kimura et al., that was also in that table. And so let me look at a day. So this is a day, right ascension declination. In red are the places in the sky that set for a very long period. In white are the ones we don't see because they don't set at all. And then this whole thing will be sort of 30 to 50% cut out by the sun, because half of the sky will be on the sun direction, and we cannot observe when the sun is up. So it's going to be half of this story. As you move in time, so for example, for bursts which are weeks or months, you have time to move around the sky, and basically you see the whole sky. Okay, so you could see the whole sky for long periods, and for shorter bursts, you have half of the sky available. One nice thing of complementarity is those neutrinos that we see. So we have complementarity in energy with IceCube because we start at tens of PeVs, and that's when IceCube stops. But also because we see, so in yellow is 8 neutrino regions for POEMMA for one model, and here is the IceCube equivalent. And since IceCube is in the southern hemisphere close to the pole, well, it's on the pole, but it's close to, if you look at rotation, it still rotates a little bit around, so it has a width. But these are neutrinos for the high energy ones that need to skim the Earth, but they cannot be coming upwards from the Earth, right? So they're very close to the limb, about 20 degrees or so, depending on if you're sitting with a neutrino, you can come all the way to 20 degrees, but not more than that. So IceCube will have a limited exposure to those neutrinos, the high energy ones, and we have a full sky exposure, so it's complementary in that way. All right, so then POEMMA and the neutrino business will be both doing these 20 or above 20 PeV or so in terms of energy, the full sky, and an order of magnitude sensitivity. And these will be pretty interesting measurements for the most extreme astrophysical accelerators. All right, so the other project, so POEMMA is basically the latest, most sophisticated version of efforts that have been going back, and we heard about OWL today. So OWL is the orbiting wide-angle light collector, and what we are borrowing from OWL is large mirrors with 2 eyes, so the stereo vision. We are using from the USO collaboration, which I'm part of, the camera. So the camera for the ultra-high-energy cosmic rays is the design that was made for USO, which is, again, the Extreme Universe Space Observatory. The GEM part used to be the Japanese experiment module in the ISS, and now it is the Joint Experiment Missions, experimental missions. So we keep changing the name of the acronym. And there's lots of things happening here. So this is the first USO balloon, the SPB-1, so the first superpressure balloon with the USO technology that we launched in 2017. And then the last piece to make POEMMA what it is CHANT, which is the idea of looking for this Cherenkov emission from neutrinos from the limb of the Earth. So those are efforts from different groups that have culminated in this design. And I'll tell you a little bit more about what we're doing now, which is building SPB2. So the USO story, it begins with the idea of putting it was actually European US Observatory at one point. This is now 2000. And it has developed, and it ended up with the Japanese leadership, and it became USO, and that dropped. So anyway, it's a long story. But the development of the camera has been pretty steady, and we've used it on the ground in the telescope array, and that's called USO-TA. We've had an overnight balloon ride in 2014 called USO Balloon, and SPB-1. We now have mini USO, which is inside the ISS, so we're looking, it's not big enough to look for the ultra-energy cosmic rays, but it's big enough to see what the backgrounds are from space, which we didn't know. We could estimate, but we hadn't measured. And SPB2 is what we are building now to fly in 2022. K-USO is the idea of bringing some sort of USO on the outside of the space station, and this is being led by the Russians right now. And finally, POEMMA is what we just discussed as the future mission. So the overnight flight, USO balloon, in 2014, so here's the balloon, there's the payload, looks like a very large refrigerator. And it was a refractor looking down with the camera, and here is an actual measurement by USO balloon. So you see a flasher, yeah, and then a shower. So this is the shower development that we expect through this module, the photodetector module. But we didn't actually see an ultra-energy cosmic ray shower. We produced one with a laser. We sent a graduate student with a laser shooting under the balloon at night. So pretty exciting. We were a little bit nervous about insurance and things, but everybody survived. But anyway. we were, oh, don't tell anybody that we're doing this, better that way. All right, so this was the similar payload. So this is a refractor with a very wide field of view and the same camera that we use for POEMMA. This was done as EUSO SPB1. And our hope was that SPB, these superpressure balloons, is a technology that NASA has developed to have 100-day flights at constant altitude. So this would be paradise when it becomes real. For now, it's not been totally predictable, as I'll show you in a second. But anyway, so here's our mini camera from POEMMA, the same type of technology with multi-anode PMTs, 2,000 pixels, and a lot of undergraduate work. So we had undergraduates and graduate students in the beautiful part of New Zealand. And this is the launch date, which was exciting because we had 7 aborted launches and finally the one. And it looked good, but it didn't seem to be totally perfect because the balloon had a leak. So here's what the balloon looked like as a function of time. So we left New Zealand and we had 2 reasonable days, and then it started going down, so we drop ballast, we come back up again. The idea of a superpressure balloon is to sit here and not move in altitude, stay at 33 kilometers or 110,000 feet. But that's not what happened. And as it went down, you can imagine our systems freezing, defrosting. It was not fun. Eventually, we ran out of ballast and we dropped in the very near eastern island. So we have a beautiful sculpture in the bottom of the ocean over there. So the idea is that in principle, in 4 days, you could actually reach Argentina or Chile. So when the winds are that stable, they can go at 100 kilometers per hour and go in a circle. And so you could spend, many, many days, 100 days, if the balloon is stable. And that didn't work for us. We were not the first. We were the 3rd SPB to fly from Wanaka, New Zealand. The first one had no science payload and it lasted for 32 days. The second had a science payload and had this interesting loop because the winds decided to do funny things. And the second, in green is the first round, red is the second round around the pole, and it didn't quite finish the second round as planned because I think it also had a leak at the end, and we had the shortest. So we were not the lucky team. But we're building again, and we're going to go back with SPB2. So in the meantime, we built EUSO EUSO, which is the same camera now in the ISS, being used by cosmonauts to measure. There's one UV transparent window, at least one, maybe 2, in the Russian module. The US would not do that because it's bad for the astronauts. But unfortunately, the Russians don't care. They have UV transparent windows that we can use. And that's what we're doing, and the data looks beautiful. We can see lots of storms and other interesting things as background, but they're usually time scales are much, much slower than our microsecond time scale for showers. And now we're building EUSO SPB2, and we're now using mirrors and the Schmidt design that we did for POEMMA. And we're doing 2 telescopes, one looking down for the ultra-energy cosmic rays and one looking towards the limb. Actually, instead of looking for the neutrinos that I talked about, we're going to do something easier, which is look for the cosmic rays above the limb, because those will also be shining Cherenkov at us, and that's how we're going to test the technology. So by looking for cosmic rays that we know are there, we know have showers and they will have Cherenkov emission, we will be able to show that we can actually detect these things. So here is the design of each of the cameras for the balloon, and this is the mirrors and the Schmidt camera, and here's the camera that will look for the fluorescence looking down. And here's our development or evolution of our detector system becoming more compact, and these are very modular, so we can build as large a camera as we want. And one of the mirrors, which was just fabricated. So we're getting ready. And the Cherenkov will be silicon PMs, and that's being developed at Georgia Tech, and hopefully we'll be flying both systems if everybody is ready. So I hope this was an interesting conversation that we had about what can we do about the highest energy phenomena that we know, or at least the highest energy particles that we can detect. So the ultra-high-energy cosmic rays will definitely be something that we still don't know the answer. It's still interesting, and it's so extreme that makes most models not easy to sort of check on all the different measurements. But we do need a lot more data above 10 eV, which is what we're trying to do with both balloons and with the space mission. The idea is, to really improve the statistics at the highest energies, and at the same time, I think if we can combine that effort, which would be guaranteed science, we know they're there, we just want to have more of them, with things we don't know, which are the neutrinos, I think we have an interesting mission in the future, and to show that that can be done, we need to have both technologies developed. One, I think, is pretty mature. The other one, there's no showstoppers we could expect, except for the fact that we haven't used them yet. So that's what we're working on right now. And then the goal in the long run is to study new astrophysics and physics with these missions. So thank you very much.
Well, thank you very much, Angela, for telling us about some extremely exciting extreme astrophysics, and also the heroic efforts that are being made and being planned to actually answer some of these questions. Let me ask the audience if you have any. Giorgio.
I have a couple of questions. The first thing is
To be fair to you, the fun part is when this thing gets overhead and this lucky guy has to get it out. So this is the video of our launch, just in case. Many people have seen launches before, and this is a nice one. So that guy gets to be lucky and figure it out. Let's see. Last time I saw it, he got it just right, but it could be. All right. Sorry, just to be fair to your question, because at least I would be watching. Yay. Okay, the rest is boring. Go for it.
yes. Another question. I thought you're supposed to follow the thing.
No, that
the thing is going with this kind of truck. Follows.
That's when things got destroyed, right? Sometimes.
That's tricky. This seems easy, actually.
Yeah, this is how we do it today.
So okay, the first question is, how is it to calibrate, particularly the neutrino thing, which is so far away and so huge? You have like a gigantic laser that shoots up in the atmosphere or something?
I think direct calibration from a laser might be hard. We certainly have those at UOJ, and we have done the laser just like in the flight, right, under the balloon. But that is nearby, right? So if you want to go to the other side of the Earth or the other side of the US and calibrate, it's much harder. So I think the best way to calibrate is to use cosmic rays above the limb, because then they are producing the exact same signal, but they're just, you point up and you see what you expect to see, and if it is the same thing, you can point down, right?
Right, so you're connected to the spectrum to see.
Yeah, at the highest energy possible. So I think you use the natural calibrators. There is one question related to calibration so Cherenkov, the fluorescence is easier because it's a line, it's a video, right? And so you know that it's hard for other things to do that. For the Cherenkov, it's pretty much a pixel that gets really hot.
So you just see a flash.
Yeah, so you do a time profile of that pixel, but you don't want to have one pixel. So what we do in the balloon is to develop, and you could do that in POEMMA, but we didn't implement on the one try at Goddard, is to have a bifocal mirror. So you have two pixels that you know which ones are related to which, and both of them have to fire at the same time and have the same profile. So you have two measurements in the same place. So that helps a little bit. And if you have both eyes, then you're in better shape. Right? So you have four measurements of the same thing.
Dan.
So with the POEMMA, how critical is the formation flying of the spacecraft to the sensitivity?
Yeah, so so we have two types of flight formations that we would like to implement. But suppose you ran out of fuel and you just sit there. Then the mode of detections are not bad at all. Right? Because you're at 525 kilometers, and we did that for Genu. So basically, the probability that you're having a showers for the energy cosmic rays close to the ground is better than if it's far away. So you get a plane, and you say, you put a probability for that shower to be coming from closer in, and for example, the distribution in the sky, it doesn't make much of a difference. For the X-max, which is the maximum of the shower, the difference between proton and iron, that would be problematic. So in our planning, we want to do as much of the composition measurement earlier in the mission, because if one of them goes poof, we'd be out wanting to do the rest. So that is the most important. The stereo is really important for the composition, but not so much for the distribution of the sky.
Roger?
Do you have background signals to worry about from thunderstorms or human activity or anything like that?
Yeah, so, you know, there are a few, the Mini EUSO and TUS, which is another even higher up telescope. We see a lot of these elves and, you know, transient luminous events, and we seem to study them to the level that we know most of their structure, and they're all on the millisecond time scales. Nothing is happening at microseconds that we could find. So the timing and the shape, the morphology, usually they have spherical things coming out of some place on Earth, right? I mean, we're up and then you have this, something happens and light is spreading around. So there's shapes and times which are very different from the microsecond lines that we expect. So that's one way to tell them apart. For the Cherenkov will be a little harder because, you know, it's even faster, so the 10 nanoseconds we don't expect something to be happening. But you have to imagine something very bright that could move that faster through the view and being, you know, sort of in one point, so this one pixel that gets hot, or even a cosmic ray that hits a pixel. So those are the ones we know we should be avoiding, and that's where the bifocal comes in, or even 2i measurement.
Right at the back, I think.
Oh, my question was exactly about hers.
Okay, all right.
Could you elaborate on what current theories for how we get these 10 to the 15th EV particles?
The 10 to the 19 electron volt particles, right?
10 to the 15th,
Yeah. All right. So, you know, we know they're extragalactic, kind of, right? And it would be hard to make them galactic. And we know their composition seems to be a little more easy to explain in the sense that they're not protons all the way to 10 to the 20, otherwise it would be harder because you need the accelerator, the maximum of the energy of an accelerator goes as a charge, right? So what you needed to explain a 10 to the 20 electron volt proton is, you know, 26 less complicated to do it if it's iron. So people here are looking at clusters and shocks in the intercluster medium, in the, you know, those kinds of accelerators. The more traditional folks have looked at AGN acceleration, and I'm one of the other radicals at the other extreme looking at newborn pulsars or, you know, GRBs and things like that as also possibilities, right? So it could be very compact things that happen or very large things. The magnetic fields have to all keep those particles in the accelerator, so there aren't too many of these objects out there. So it's neutron stars, AGN, gamma ray bursts, and clusters of galaxies. Those are the 4 places that people look.
Perhaps I could just...
That's a big range,
Yeah.
which is why we need more data.
Yes, so...
I mean, as well as, you know, the tremendously interesting astrophysics puzzle layers to answer your question, there's also the possibility that the whole suite of experiments at these very high energies can teach us some fundamental physics, and that's often touted in proposals and so on. How realistic do you think that is in practice, and which do you think are the best bets for finding something that really tells us fundamental
Right,
physics?
I'm an optimist, right? So to me, if you go down to, remember the big cliff in the spectrum, right? So it's going down, which means you probably reached the maximum of the astrophysical accelerators, so it's the perfect time for other things to show up, right? So other things could be decays of relics from the beginning of the universe, it could be super heavy dark matter. I mean, there are many ideas that were there when we couldn't explain the data, but now we can explain the data with astrophysics, right? So this, you know, back when these things were built, there was a discussion of if the flux never had a turnaround, that it kept going, and that was basically bad energy calibration, right? So now we know it does turn around as expected, but the reason for it turning around is not what people expected. It's not the GZK probably, it's probably the maximum energy of accelerators. So now we have, well, what happens next, right? And if we don't go measure, we won't know.
You think the actual prosaic business of measuring, of modeling the showers could actually have some physics in it as well. That's fundamental.
That's another, yeah, so neutrinos for sure, right? I think neutrinos are very clean, so if I'm a particle physicist, I'd rather get the neutrinos than the other energy cosmic rays, because, you know, we're looking at a lot of hadronic processes down the tube, which is not, you know, very easy to make fundamental discoveries. But I think for neutrinos is a different story, right? So you could even, so the dream would be you know the flux of neutrinos because you figured out who's the accelerator, and then you just follow it as it goes down the Earth, and that means different interaction path lengths, and then you know what the physics is at the highest energies, right? And if, you know, the Anita event, there was a weird neutrino coming at a wrong angle, that can only be if there's physics beyond the standard model. And even that doesn't explain those events, but that's the kind of interesting thing one can do.
Well, anyway, let's thank Angela for a wonderful talk, and wish her the best in her project.
All right, 2 of them here. This